Okay, one more question maybe. Yeah.
Can you give us a little bit of background other than the digital modes on what you've done? I was in Puerto Rico a bit ago and saw at Arecibo what you had done and gotten your prize for it. Just give us a little bit, because there's some people here who aren't.
Well, I mean, don't get me started. I'll talk for another hour. Professors are programmed to speak for 50 minutes, you know. All right. So the Nobel Prize was for the discovery of an orbiting pulsar. A pulsar is a neutron star, a star made not of atomic matter like the sun, but of nuclear matter. So it's like taking atoms and crushing them down to the size of the nucleus. And an atom is way bigger than, the cloud of electrons around the nucleus is most of the space. So if you make a star like the sun into a neutron star, it's only 10 miles across. A teaspoonful of neutron star matter would on Earth weigh about 1 billion tons. This is really dense. Anyway, so there are lots of interesting things about a neutron star. Was first hypothesized in the 1930s, soon after the neutron was discovered as an atomic subparticle. But it was not known that it would actually exist. It seemed like the laws of physics would permit such things to exist. They were not actually discovered until the 1960s, when we were able to put satellites into orbit carrying X-ray detectors and things like that. And we first got signals then from things that looked as though they were consistent with being made of nuclear matter. Pulsars were discovered in the late 1960s. Pulsar, I said, is a neutron star. It's strongly magnetized and it spins rapidly. If you spin a magnet, you've made an electrical generator. So pulsars generate huge electrical fields above their magnetic poles. That generates radio noise, and a spinning radio noise beacon is like a lighthouse. So if you're located in some direction over here in space on the Earth, and a neutron star goes around like this, whenever it's pointed toward the Earth, you might get a blip of radiation, a pulse. Yeah, when it's pointed at you. And so pulsars are impulsive sources of radio noise. They keep time very accurately because this thing is spinning freely in space, no friction or anything to slow it down. So pulsars keep good time. And I started this project when I was an assistant professor at the University of Massachusetts. I talked a graduate student into working on it with me, and we shared the Nobel Prize 19 years later. That's a pretty good way to start your professional career. Not bad. But anyway, we had basically what we did was design a pulsar detecting machine that used what we then called a mini computer. It was something about the size of a refrigerator and weighed about 800 pounds, and we had to air freight it down to Puerto Rico from Massachusetts. But we had programmed it to detect these impulsive signals. And we were fortunate enough, I realized that one of the really important things which hadn't been done was to find a pulsar orbiting around some other object so that we could measure Doppler shifts and therefore get an indication of its mass. And we did not imagine what would actually turn out to be the case, that not only did we find that, the orbit was very tight. It goes around the other star in about 8 hours. So 3 times a day, this thing goes around the other object. So it was clear that this was probably 2 neutron stars, one of which we detect and the other one we don't, but they must be that because an ordinary star like the sun wouldn't fit in this orbit. And furthermore, the velocity of the motion of the orbit was huge. It was 300 kilometers per second maximum. That's about 1/10% of the speed of light, so that relativity is important. Ordinary Newtonian physics would not explain this orbit, but relativistic physics does, Einstein's theory. And what this enabled us to do over time was to establish that this system was radiating gravitational waves. You may have remembered the splash in the newspaper 2.5 years ago when a group at Caltech and MIT detected gravitational waves with a big instrument that cost $500 million. That instrument would never have been funded if our experiment had not worked, because basically we showed the U.S. National Science Foundation that these guys were not chasing a will-o'-the-wisp. There was actually, we proved that gravitational waves actually exist. So that's what they...
Telescope, how
The telescope, well, what we wanted to use was the biggest radio telescope that we could get our hands on, and that's the one in Puerto Rico. It has some limitations. The dish is fixed, attached to the ground. You steer it by moving the feed antennas around, so it has limited steerability. But this really nice relativistic pulsar goes straight overhead in Puerto Rico, so we could measure it for a few hours every day. It was a relativity experiment handed to us on a silver platter, if you like. It was really great. Okay. Okay.
Thank you.
Thanks.